definition. This is to HUN-REN in 2006. Can everybody read this? Good. All right. So we say that if we have two HUN-REN knots in some contact manifold, YC, and just a quick reminder for those of you who need it, HUN-REN means that the tangent vectors to each knot lie in a contact distribution along the knot. And so we say that these two knots, K0 and K1, are Lagrangian covariant. If, well, we can look at the symplectization of Y. So that looks top plotted blue like Y times R. And it has a symplectic form on it. D of e to the t times alpha, where t is the R coordinate and alpha is the contact form for the contact structure. So we see that they're Lagrangian coordinate. If we can take a copy of one knot of, I guess, K naught on one end and K1 on the other, and we can find some Lagrangian surface. Call it L. Maybe it has higher genus, maybe not. But if we can find some surface L, which is Lagrangian, such that for t sufficiently large, L intersected with Y times all sufficiently negative real numbers is equal to K0 times that interval, and similarly at the other end. So for all sufficiently large time, L just intersects the Lagrangian in a cylinder over the knot K1. And that's just for some t really big. And so the question is, well, how can we tell whether two knots are Lagrangian coordinate or concordant, concordant being the specific case? How can we tell if two are coordinate? Well, we can try and construct it explicitly. Maybe that works, maybe it doesn't. And if it doesn't, we might want to try and find instructions. So the question is how to find instructions to Lagrangian coordinates. And
that's not a symmetric relation, is that?
It is not a symmetric relation. I guess there are examples that have been claimed, for instance, the Legendre unknot is concordant to 946 either that or its mirror. It's been claimed by HUN-REN that the opposite is true, although I don't think a proof is written up yet. I will consider embedded coordinates.
So how come this definition is so new?
Nobody thought to write it down, I guess, or nobody thought to say anything about it. I don't. It seems like an obvious relation to think about, but somehow no one did. So anyway, so there are some instructions. HUN-REN showed that the classical invariants T, B, and R, which are just integer valued, are, well, they're Lagrangian concordance invariants. If you have a higher genus cobordism, it preserves R, but it drops TB by twice the genus. And you can come up with some other instructions from the Legendre contact homology. You would hope maybe that if you write down a natural enough invariant of the Legendre knots, that it gives you some kind of obstruction to concordances and higher genus cobordisms. Maybe it gives you maps on knot homology or something that carry a Legendre invariant to another. And so specifically,
Like when you say concordance invariance, this means there exists a concordance in both directions.
No, I mean, I guess what I mean is I want some, maybe that some Legendre invariants behave naturally under cobordisms, that they induce maps. And those maps may only go in one
I'm
direction.
just wondering about that specific statement about T and R.
Yes. Well, concordance is not symmetric, but if you have a concordance, it preserves both of those. So TP or R not being the same is an obstruction. Not a very good obstruction, but for a while it was the best we had, I guess. So around maybe 2007 or so, there was one invariant defined by Risto, Rizwa, Stipschitz, and Sabo of Legendre knots, about 07, an invariant that we'll call L hat of K, which was in the non-core homology, the hat version, of Y with the opposite orientation, K. And this is a good invariant of Legendre knots. It lets you distinguish lots of things. But you might ask, well, is this natural? And I won't get into the original definition. Is this invariant natural in some sense under the Lagrangian cobordisms? And the original definition of this invariant, you use open books, you write down an open book decomposition where you can see the knot K, you do some Hagar homology and outplots an invariant element. But the problem, well, I don't want to say it's a problem. The current shortcoming in our knowledge about Hagar homology is we don't know much about how it relates to symplectic cobordisms. So, you might ask this question, is it natural under Lagrangian cobordisms? And maybe it's the way it's been defined, we don't really have a good way to answer that. So the goal was, well, one goal is to find a way to answer this question. So for that, we can use maybe an alternative formulation, and I shouldn't say it's alternative because I haven't given you an original formulation, but one way to describe this came from work a few years ago of Stipschitz and Bertich, 2008, 9, maybe after the original paper there. They give a definition or a construction of this loss invariant in terms of suture homology. Namely, if you look at the complement of a Legendre knot, it has a standard neighborhood, which here's a picture of the boundary of it. You can think of it as a convex torus with a pair of dividing curves that are determined by the Thurston-Bennett framing of the knot. So maybe this direction is a meridional direction, the horizontal one, and the vertical direction is the contact framing. And to that, you can maybe attach a bypass, half an over twisted disk, along a curve that looks like, maybe I should use a different color, along a curve that looks like this. And when you do that, how does the boundary of the knot change? The boundary of the knot complement, how does that change as a convex surface? Still working? Well, now the dividing curves on the boundary don't become meridians. So it's still you still have the same framing, but now we sort of flip the dividing curves over. So this gives you some new contact structure called YK, so comma CK, and you can write down a contact invariant. Well, so using a contact invariant in suture for homology, you know how it does manage. So that to a contact structure in a suture manifold, they associate a contact invariant called pH of the contact structure. in Sivek homology of this manifold yk comma gamma k being the dividing curves. Like that. And since the dividing curves are meridians in the knot, and there's a pair of them, they should be optically oriented, this is naturally isomorphic to the knot form homology minus y comma k. And the theorem that, let's write it up on this board, one of the theorem that was proved by Stipchins and Vertex was that this invariant here, this contact invariant, is identified under this isomorphism with the loss invariant of k. So, one reason for the last couple words in this everyone's talk, in Sivek monopole homology, one reason you might want to use it to study things like the Legendre knot invariance is that monopole homology is known to behave well under, for instance, exact symplectic copordisms, and you might hope to apply that here. So, I guess for the next couple minutes or so, I'll introduce people to what monopole homology is and show why this is a useful tool, like why this might be appropriate to solve this problem. So, get my notes here. Okay, so what is monopole homology? Well, the quick one-sentence definition that sort of hides a lot of information, doesn't really say much, is that it's basically doing Morse theory for the Chern-Simons-Farad functional on a three-manifold. Namely, from Tom's talk yesterday, you remember that instanton homology is sort of a version of Morse homology for the Chern-Simons functional. For the Chern-Simons-Farad functional on a three-manifold, suppose we have so a three-manifold Y and a spin C structure. Well, what does the Chern-Simons-Farad functional compute? You give it two inputs. There's a spin C connection on that spin C structure, which you can think of as a rank 2 Hermitian bundle over your manifold, together with the notion of Clifford multiplication. So I'll write that bundle as S sitting over the manifold Y, and gamma is, C is a section of that spinor bundle. So you associate to some integral, sum of terms. Maybe 1/8. There's a term coming from the connection. Looks like something like the following. And then there's a extra term coming from the spinor, the section of that bundle S. Volume. And so what the notation means here, when there's a T superscript on a connection B, that means that it's that's the induced connection on the determinant bundle of S. So you write down this functional, and it turns out that the critical points of this look like something fairly familiar. They look like solutions to the Sivek equations. So critical points of L are solutions to the Sivek equations, which I want to write down on a three-manifold, and gradient flow lines of the Chern-Simons-Farad function also. Solutions to the equation again, in this space of connections and sections of a spinor bundle, are basically one-to-one correspondence with solutions to the four-dimensional side derivative equations. On the cylinder y times r. So these look like very familiar equations, and after a lot of analysis, you can get a homology theory by basically, like I said in that first sentence, doing Morse theory. There are a few caveats. One is that you have to divide by a gauge group action. So that looks like maps from the manifold y to u of 1, and that acts on the space of connections times like that, and so you divide by this action, and then the action isn't free. They're so-called reducible solutions. So you have to actually blow up the space so that the G action becomes free. And then what you do is then you do Morse theory basically on that quotient. And the result is you get some homology groups. I'm going to stick with a particular kind here. So the result that I'm using for this talk is you get a group HM2 of Y in a spin C structure. And for those of you who like figure out homology, you can think of this as HF plus of Y and S. This is, for this I should cite the recent work of Colin, Gigi, Honda, and simultaneously Goodwin, Lee, and Towers. So that's roughly what monopole homology is. This is sort of an extremely brief, extremely vague overview. But now, how do you do this for sutured manifolds? So, and I guess I shouldn't attribute it too while I'm here. The canonical reference for all of this is the book by Kronheimer and Murka, Monopoles and Green Manifolds. So if you don't have that on your Amazon wish list, you should run home and do that after this talk. All right. What's that?
I'll give you 21 seconds.
Thanks.
It's a great book, you should all buy it.
Anyone else have praise for it? All right. So now, that was everything I said there was for closed three manifolds, and you might want to maybe generalize this a little to sutured monopole homology. So this is sort of an analogous version of core homology to so-called sutured core homology, which was defined by Uas in 06. And the idea is, well, suppose we have a balanced sutured manifold M. Thanks. Should include sutures in there. And what do I mean by balanced sutured manifold? Well, it has to satisfy a couple things. One is that this thing I've denoted gamma is an embedded multi-curve, a one manifold in the boundary M. Okay. Another is that you can write the complement of that curve gamma as a disjoint union of two surfaces, R plus and R minus, whose boundaries with positive or negative orientation are actually just equal to that curve gamma. The third condition, this is about being balanced now, is that the Euler characteristic of that surface R plus has to be the same as the Euler characteristic of R minus. And the fourth condition is that the map from the so-called sutures, the components of gamma, to the components of the boundary is surjective. So these are, this is what a balanced suture manifold is. Just some quick examples. One we've already seen in the initial motivation, something denoted often y of k, where k is a knot. You just take the neighborhood of the knot out of your manifold, so y minus the neighborhood of k, and then you take a meridian and another meridian with the opposite orientation. So here's a picture of the boundary of the knot complement. You take one suture oriented that way, another suture oriented the opposite way, and then, from this condition here, the regions R plus and R minus should look like, R plus is the annulus on top, R minus on the bottom, and clearly they have the same Euler characteristic for both A and I. And another quick example is maybe even easier, y of 1, as it's written, which is just y minus a ball, and a single meridional suture on the boundary of that ball. So there's gamma. Gamma here. And again, R plus is the disk on top, R minus is the disk on the bottom. So these are examples of balanced suture manifolds. And once we have one of these, we want to assign it some sort of homology group. So here's how we might do that. Sorry, I forgot. One more important example. So suppose that y is a contact manifold with boundary, and that the boundary is a convex surface. This is a C infinity generic condition. You can just perturb it smoothly so that it's convex, meaning that it's transverse to some vector field whose flow preserves the contact structure. So then, y, comma, the dividing set of the boundary is a balanced suture manifold. And we can, from this is like a basic exercise, maybe I'll write it as such, even though this isn't a mini course. You basically need to check that in order for it to be balanced, well, every component of the boundary contains dividing curves, and the two regions R plus and R minus, the positive and negative regions of the surface, have the same Euler characteristic. Basically, because the Euler class of the contact structure evaluates as 0 on the boundary of the manifold, the boundary of the manifold being 0 in homology. So contact manifolds with boundary are great examples now of balanced suture manifolds, things that might have homology groups associated to them. So now I'll define suture monopole homology. This is also two-parametric. And Rivka about 2008. And here's how we construct it. Well, it's an abelian group. You have a suture manifold and gamma. We get some group SHM of M and gamma constructed as follows. So the first thing we do, I'm going to mostly draw pictures because in my experience it tends to be a lot hopefully easier to see that way. So step one is we pick a surface T with boundary such that the components of the boundary of T are in one-to-one correspondence with sutures of our suture manifold. So for example, maybe our suture manifold is a solid torus or something, and it's got two sutures, just these curves here. And we take a surface with, well, there are two sutures, so we take a surface with two boundary components. Well, we may want to have large genus. I'm not going to spend a lot of time discussing that. But what we do with this surface is we glue a picking up version T times I to the manifold M. And what we do is we send the boundary of T times I to neighborhoods of the sutures. So in this picture here, I'm going to thicken it up. Now there's these two annuli, boundary of T times I. I'm going to send one of these annuli to a neighborhood of this suture, and send the other annulus to a neighborhood of the other suture. And the resulting manifold call it Y prime. It has a boundary of two components, which I will call, I'm going to call them F plus and F minus. If I still can call them R, I apologize in advance, but usually I call pretty much everything R, so I'm trying to not be confusing. And in fact, F plus is diffeomorphic to F minus. The reason for that is that, well, we have this balance condition that the Euler characteristics of R plus and R minus, which on this diagram are maybe here and here, those Euler characteristics are the same. And in the two boundary components of the new glued up thing of Y prime, well, one of the components contains R plus, the other one contains R minus, and the complements of those are copies of T. So the results that F plus and F minus, these two boundary components, still have the same Euler characteristic, but now they're connected. So they have to be the same surface. All right. So step two, once we've done that, is we pick a diffeomorphism. Like I said, F plus and F minus are diffeomorphic. So we'll pick a diffeomorphism. Call it H from F plus to F minus. And we'll glue by the diffeomorphism. So we'll let Y of n comma gamma, some closed-up manifold, be equal to, well, it's just a manifold Y prime over the map X is identified with H of X, the relation. And inside the surface, we have inside this manifold, we have a distinguished surface, R bar. So what that manifold is just the image and the quotient of F plus. And so now we have some closed-up manifold Y, and again, it no longer has a boundary. And once we've done that, we can finally just define the sutured manifold homology of M gamma to be something written occasionally HM2 of Y M gamma, the closed-up manifold. I don't know how to pronounce this, with respect to R bar, which is defined as the sum of the homology in certain spin C structures. These are the so-called top spin C structures on Y. They're defined by the first term class pairing with that surface R bar as twice the genus minus 2. Up to sign anyway. I think I got this sign. And this seems like kind of a funny thing to do, but it's the right thing to do. I guess that it can be true. That this is independent So I'm gonna just work out a really quick example. Let's just take the standard ball with a single meridianal suture. I'm gonna round some edges a little bit so it looks like a disk times an interval. And here's the suture. So step one was we take a surface with one boundary component, multiply it times an interval, and glue this annulus here to the sort of annulus I've drawn vertically. And the result is that the manifold y prime, well, it looks like a genus 2 surface times an interval. And I've sort of drawn the original ball sitting in here. Alright, so that's just sigma 2 times I. And then, once we have that, well, the boundary is a genus 2 surface on top and a genus 2 surface on the bottom. So, from step 2 of this procedure, we maybe pick H to be the identity on that genus 2 surface. So then the closure manifold y and gamma is just sigma 2 times the circle. Well, we gotta just sort of close that up. And that the surface or bar inside of it is just sigma 2 times the point. And then it's a fairly straightforward computation to see that SHM, the suture monopole homology of this ball, well, that's monopole homology of sigma 2 times S1 in the top spin C structure. Top spin C structures, and from thinking about the separate wave equations, this is free of rank 1. You can, I guess, write it down so that there's a single solution that generates the chain complex. So do people more or less follow what I've done here? Okay. So, like I said, the aim of this talk was to, think about contact geometry in this, in this suture monopole homology world. So, what I'd like to do is define the contact invariant as follows. Given a manifold y with boundary and a contact structure with dividing curves gamma on the boundary, I want to associate some element, call it capital C, that lives inside the suture monopole homology of minus y comma minus gamma. Just like the Hayward-Floer sutured contact element that I mentioned earlier, the 1 by 100 Desimotage. And so the idea is, well, we construct the sutured monopole homology by embedding m gamma in some larger manifold, y at m gamma. So maybe we can take the contact structure that we have on a sutured manifold and embed that inside a larger contact structure. And once we've done that, well, monopole Floer homology, HM2, comes with a contact invariant for closed spinning manifolds. So if we set this up correctly, maybe we can let our contact invariant just be the contact invariant of that sort of larger contact structure in the closed manifold. And, if we play our cards right, we'll have an invariant. So, how can we do that? Well, remember what step 1 looked like, constructing these closed sutured manifolds. We have our sutured manifold now. Maybe it comes with a contact structure, and the sutures are the dividing curve. Okay. It should have worked to define a contact element. So we had to pick a surface T, and find some way to glue T times I onto our original manifold. And since there's a contact structure on this guy, we'd like to put a contact structure on T times I as well, so that when we glue it together, they're compatible, and we get a contact structure on the bigger thing. So what we'll do is, we'll take a set of arcs, a so-called arc decomposition. Maybe this is not standard terminology, because what I actually want is a set of arcs that will cut T into an annulus. So A1 through A negative T, so that the complement is an annulus, like I said, just one times I. This is a genus 2 surface, so I usually can't really draw the arcs correctly, but I'll try my best. Maybe you have one arc like that, another one like this, and then I guess you need 2 more. Something like that. Is there a problem in decomposition? There's too many, yeah. Right. Okay, so now we have 3 arcs that it should be, and the complement of them should be an annulus. And so what we'll do is we'll put a contact structure that doesn't depend on the I direction, so it'll be I invariant. So we'll put that on T times I. So that the positive region of T times 1 is a neighborhood of these arcs. So I'm going to draw a quick example of the genus 1 surface because that's a little easier. So if this was our arc decomposition of a punctured torus, we would have a contact structure on the genus 1, the punctured torus times an interval, so that the so-called positive region of the boundary is just, well, a neighborhood of that arc. And so the dividing set ends up being 2 parallel copies of the arc decomposition. And because we want this to be I invariant, well, I've specified it on T times 1, and it's going to be the same but with signs reversed on T times 0, and on this little annulus in the middle, we get sort of vertical strips whose endpoints are interlaced with the endpoints of the dividing curve on top. There's standard effects on the
Is gamma plus the positive region?
Sorry?
Gamma plus is the positive region?
Gamma plus is the positive region, right? Its boundary is going to be the dividing set. And now that we want to, or now that we have this contact structure, we need to glue it. As before, we glue these annuli to neighborhoods of sutures on our contact manifold, but we do it by perturbing slightly. So here's a local picture. This is on Y, on the boundary, in fact. It's a neighborhood of a suture, or a neighborhood of a dividing curve. We'll call that gamma. And we just sort of, we take this curve and wiggle around a little bit, so it intersects itself transversely a few times. And we let that be the actual suture rather than the dividing curve itself. This doesn't change anything topologically, but the point is that the gluing region here had some, the dividing set with some arcs that went from one boundary component to the other. And so if we fatten up a neighborhood of this suture here, now we can see that the dividing curves actually look exactly like that. And the number of times we wiggle it back and forth is just determined by how many dividing curves there are on this angle. So And then the last step, well, the second step, I guess, was we had to pick a diffeomorphism from between the two boundary components, F plus and F minus. And now, well, F plus and F minus come with their convex surfaces in a contact manifold. They come with dividing curves. So we just needed to send one dividing set to the other dividing set. And the result then is a contact structure on a closed manifold. So it's a manifold wide 1 gamma with before and some contact structure of C bar. And we take the contact element, the contact invariant, to be the usual closed monopole element, monopole contact invariant of this closed up contact structure. And that, it turned out, will live in the monopole homology of minus n comma minus n. So, I should work out an example and maybe say something about why it's invariant. I don't have much time to address the invariance, but let's work out the standard 3 ball again, except now it has a contact structure, so we'll call it a Nordu ball. The standard type contact structure on A3. We can draw it the same way as before. It has a single dividing curve on its boundary. We can glue in, say, a genus 2 surface times an interval right before, and we needed to take an arc decomposition, something like this. And the result is that y prime, if we're careful about this, y prime comma c prime is just like before, the genus 2 surface times an interval. And it has some contact structure that's high invariant. And what does that contact structure look like on one of these genus 2 surfaces? The negative region is topologically an annulus. That's why we picked an arc decomposition, something that's fitted into an annulus. So now this is the negative region, this is the positive region. And the last step we glue together, again by using the identity map. So, and I didn't have that plus that minus. And the result is y m gamma equals, again, genus 2 surface times a circle. The contact structure on it is now S1 invariant. Because of this I invariant, we didn't do anything new when we glued the top to the bottom. And on any particular surface, sigma 2, again, the dividing set is a parallel non-separating curves, so the negative region is the annulus between them, and the positive region is everything else. And now we sort of, I guess, hit this with a hammer. We use a theorem, a special case of a theorem, Kruger and Wendell, which says that this contact structure is weakly symplectically fillable. So in particular, we have a contact element that we associated to this standard contact structure on the Dirac ball. And if we work over an Novikov ring, which I'll write lambda, maybe over a Z mod 2, and the contact element in that Novikov ring is non-zero. It's, in general, a primitive element since it's weakly fillable. So we can say that it equals up to automorphism the element 1 inside our coefficient. I haven't said what we're twisting by. It's, you have to take a curve in your surface that's maybe dual to the dividing curves, and then you can construct a symplectic filling of, well, a weak symplectic filling. Symplectic forms concrete with that. So, all right. So I've now shown how to construct the invariant and worked out, just about the only example we can really explicitly hope to do. Are people with me? Okay, great. Because if you you have any questions, feel free to interrupt. So I'll say just a few words quickly about invariance. The theorem that John and I proved is that this contact structure is really an invariant. It only depends on the contact structure. And the proof, we need to check that it's independent of a couple things. So, one is that arc decomposition inside the auxiliary surface, the arc sweepings to cut it into an annulus. Another thing was the choice of diffeomorphism that we used to glue things together when we were building a closed manifold. And then the third thing is the genus of that surface T, which maybe is better expressed as the genus of the surface R bar instead of closed manifold. So we need to check each of these in order to say we have an invariant. So I'll say just a few words about that. For one, well, think about maybe not the arcs themselves, but let's see the core of the annulus that we get by cutting along those arcs. So, T minus D minus I. Maybe we pick another arc decomposition. So we'll call that A prime. Then we get another core, C prime. And so the contact structure on T times I, if you think about it, is really determined by that core. That's what matters in there. So the core is just sitting inside here as some simple closed curve. Maybe it's C in this picture, and maybe C prime is, I don't know, it goes around the other component in the other picture. And, it doesn't look like I've done much there because, well, taking a simple closed curve inside a surface of, I guess, of genus at least one, any two choices are equivalent. So we can take a diffeomorphism from the surface to itself, which sends C to C prime. And once you've done that, well, then this extends pretty straightforwardly to a contactomorphism. From, well, T times I to T times I will be the choice of contact structure. So there's sort of, no real information going on there. For the second step, for the choice of diffeomorphism, well, we can take any two different choices of diffeomorphism and break up their difference into a union or a composition of gain twists. So we use two gain twists. Namely, we cut our surface, we cut y and gamma along some curve C that sits in the surface R bar, and we reglue by a twist around C. And for that, we need to use a theorem. That was recently proved by HUN-REN that if you have an exact symplectic cobordism, so say we have contact manifolds y minus C minus and y plus C plus, and we have a symplectic cobordism between them like this. Well, cobordisms induce maps on monopole phenomenology. So it induces a map from HM bar of minus 1 plus to HM bar of minus y minus, sending the contact invariant of one to the contact invariant of the other. And so an example of an exact symplectic cohort zone is a Legendre surgery. This corresponds to attaching a two-handle, and the two-handle can be given economical symplectic structure. So in the case of Dane twists, well, all we have to do is realize a Dane twist about C as a Legendrian curve. And then we do a positive Dane twist. So let's just say positive for now. The negative case follows from sort of doing this backwards. Then the coordinate map sends, well, SHM of minus y1 minus gamma 1 to SHM of minus y2 minus gamma 2, and it carries the contact, well, call it maybe C1, the contact element we get that way, to the contact element we get the other way by redoing the Dane twist. And then by the search of exact triangle, that says this map is an isomorphism. Because this map is into the search of exact triangle, where the third element is a sort of zero-frame surgery along that curve. And that zero surgery compresses the surface R bar, so you can apply an adjunction inequality in homology to say that that third term vanishes. So that takes care of independence under the arc decomposition and the choice of gluing, and then I'm not going to say anything about the genus because there's no time. So let's get back to the original question that I asked in the last few minutes. Yes?
Your curve around which you do the, I might have not understand, but the curve around which you do the denting, does it intersect the dividing set or not?
It does not, you can make it non-intersect the dividing set because the gluing map is required to send the dividing curves to dividing curves. So if you change your diffeomorphism, you're changing it by some diffeomorphism in the surface that fixes those curves. And you can break that up into Dane twist about curves that avoid it. So that's how you make sure it's a Legendrian surgery.
So I have another question.
Okay.
If I understood correctly, there was some kind of arbitrarity in choosing the curve around which you took the suture at the beginning. How do you prove that this does not depend on what you choose?
You mean like when I had to sort of wiggle things to glue it all together? Yeah, so you can check that that doesn't affect it either. It's just sort of a tedious but kind of elementary argument. You keep changing the contact structure inside like tight free balls, and so you know that any two choices are related basically by an isotopy. So there's sort of, any two sort of choices of wiggling can be made the same, can be made to be isotopic.
No, that was not the weekend. It was what? And I will ask you what I did.
Okay. All right, so let's talk about the Lagrangian concordance again. Well, given a Legendrian knot, K inside the contact structure, we want to sort of imitate the loss invariance. So we'll let, I'll call it the script elegant of K, be contact invariant of the structure YK, CK that you get by gluing the bypass onto the knot complement. So that the sutures are ready. We'll define it that way. And what I claim, this is about, I don't know, a theorem and a half because it's two separate statements. And, well, I have both statements in one proof, but not the second proof. So it's in progress. So if K1 is Lagrangian concordant, or Lagrangian, concordant to K2, then there's a map from the sutured monopole homology of minus y comma minus K2 to the sutured monopole homology of minus y minus K1 that sends the Legendre invariant of K2 to the Legendre invariant of K1. So Lagrangian cobordisms give you a map in sort of the opposite direction that preserve this invariant. And right. And the proof sketch, well, there are two cases. One is when the genus of the cobordism is zero. In other words, when we have a Lagrangian concordance. Well, what we can do is, let's take the symplectization of our manifold. Inside it, we have a Lagrangian cylinder, L. And so what we do is we cut out the standard neighborhood L. I left out one little detail. We want the exact, we want the Lagrangian cobordism to be exact. And in the genus zero case, it doesn't matter. All Lagrangian cylinders are exact. So we'll cut out the neighborhood of L, and we just glue in a piece. So we take y of K1, draw a picture here. So we take 1 minus K1, and we glue in some piece Z to get the closure. There are too many Y's here. But, when we construct a closed manifold to complete the Legendre invariant of K1, we take out that complement and we glue in a piece Z. And all we do is glue in Z times I to get an exact cobordism. From a closure of K2, no, sorry, K1 to a closure of K2. And then by this theorem of Hutchings-Taubes, that exact cobordism gives you a map carrying one contact invariant to the other. So that's case one. That part is actually done. The other half that's in progress is when the genus of L is greater than zero. And here the idea is we use these sutured cobordism maps which in sutured homology we do to U-bus. The idea being here, if we have our cobordism between two knots, we can cut out the neighborhood of the Lagrangian surface. We glue in some piece here, which is something like the piece Z times I from before, and this gives us a cobordism from, on one hand, a closure of the non-complement K1. On the other hand, we get a closure of the complement of K2, union with the boundary of standard neighborhood of the knot K2. So this cobordism, once you check it as exact, it gives you a map from the invariant on this side to the invariant on this side. And then you can take a closure of the complement of K2 and construct a map from that invariant to this one by basically defining maps corresponding to the attachment of contact handles. So you can take a contact handle decomposition of the neighborhood of Lagrangian, and each of those handles gives you a map from before the handle to after the handle. So the composition of these two maps gives you the map that you want. So I'll stop there. Thank you.
Any questions?
So, I'm curious about the vertical problem. Hagar topology and ECH, there's this distinction between twisted and untwisted coefficients.
Right.
And the result of ours that we quoted, that this S1 times the continuous two circuits with this divided set is speaking of Philip, implies that the contact invariant with twisted coefficients is primitive.
Right.
The interesting thing about that example for us is that it's not strongly Philip and it's untwisted contact invariant packages. What does that imply about what you were telling us?
Well, yeah, I wondered for a while what the contact invariant would be, and then I saw your paper that the untwisted invariant was 0, and it made me sad for a while because I had to use the Nova covering, like I mentioned earlier. However, you can actually show, and we do this somewhere in the paper that's in progress, that well, when you work over the Nova covering, that had the effect of tensoring the suture homology groups with untwisted coefficients by the new coefficient ring. But there's a way using Giroux correspondence where you can sort of define an analogous untwisted invariant, and the relation of the untwisted invariant to the one I've defined here is just, you tensor with the element 1 of the Nova covering. You sort of don't gain any extra information, you just have bigger coefficients to work with. So for example, it's still entirely possible that, well, we're fairly sure that our invariant is the same as the EH invariant here at homology. So for instance, even though we're working in the Nova covering, Giroux torsion should kill it. That makes sense.
Any other questions?
So do you have like functional reality with respect to inclusions of contact manifolds?
Well, we have maps defined by inclusions of contact manifolds. In order to show that these maps are necessarily well defined, we probably need some statement about relating one contact handle decomposition to another. So it's a little tough, but for applications like this one, we were sort of happy enough with the existence of a map, and it might be very hard to say more than that. I mean, in adjustable, these agree with the Haggard floor maps here from inclusions of contact manifolds, which are natural. But again, how you prove that is not really clear.
So this situation of course is a bit different, but do you have any like long design sequence like with the general contact homology for the borders of the station generated this contact homology?
Right. I don't know anything. Like I would like to know how to relate something like Legendre contact homology and generating families to this, but I don't really know where to begin. The one exact triangle we do have is bypassing that triangle from the spatial. That's really not the same thing.
If there are no other questions,